Welcome back to Linear Systems and Signals, and this video is going to be about what we call time-invariant systems. So what do we mean by time-invariant systems? So the learning objective for this section is to determine whether a system is time-invariant or time-varying. And when we talk about time-invariant systems, we mean systems whose behavior or dynamics does not depend on the particular time at which you're using them. So that is, if I have a system, that's a box, right? The arrow goes in, arrow goes out. So if I put an input in today and I get a certain output, then tomorrow, if I put the same input in, I should get the same output. Now you might think, oh, like, isn't everything like that? Like, you put the same input in, you get the same output. And the answer is no. I mean, if the actual internals of the system might change with time. That is, maybe something is decaying or something is, say, evaporating in some kind of physical system, right? So the system inside the system internals could be changing over time, and that would be a time-varying system, in which case the same input-output pair, you put in this input x, you get this output y, you might not get the same output y from the same input x a little bit later. And so that's what we call a time-varying system. So let's look at the definition. The system H is time invariant if basically if I delay the input, I get the same delay in the output, right? So if I put in a signal x of t, whose output is y of t with that system H, and then I delay it by t0, or you could also make t0 negative, so you could start it earlier by t0. But if I delay it by t0, then I get the same output y, but now y is also delayed by t0. And the same thing in discrete time. If I have an x of n and I delay it by n0, I get the same output y of n, which was the y of n is the output for input x of n. I'll get y of n minus n0 for y of n. So I should put square braces here. Right? And a system is time varying if it's not time invariant. So time invariant is a property. If it's not time invariant, it's time varying. So we can see this pictorially in this picture here. So here we're saying this is the behavior today, how the system works today. Now, and then what we have is you delay by k, and here we delay by k. We get the same output delayed by k. So the internal dynamics of the system don't change. So a fancy way of saying this is the system commutes with delay. And so what do I mean by commutes with delay? Remember, an operation, if I call it star, if I say, A star B is commutative if A star B equals B star A. And so what we're saying is if I have a delay and a system, and the system is time invariant, then I can swap them. I can do the system first and then the delay. So remember, what we're saying is that I assume that the output y comes from the input x, and then if I delay x, I get a delayed version of y. Right? So that's x, here's the delayed version of x, and then here's the delayed version of y. But I could equally take x, produce y, and then delay that. And those two things are equivalent. So that's what we mean by the system commutes with delay. And when we get to linear time-invariant systems, which is the topic that comes up next in the course, we're going to see this commutative property is really important because it lets you swap systems back and forth, and it doesn't matter which order you do them. Of course, when you implement them, it might matter quite a lot which one you do first in terms of the complexity of the implementation. But from an analytical perspective, it doesn't matter. So this really can help you simplify your analysis and also your design. And then later on, you can figure out what are the implementation constraints. So let's look at an example. And if we want to really try to avoid confusion, that is, if you're trying to show whether a system is time varying or time invariant, what you should do is, the problem is that you put in this delay, t0, right? And what happens is you get confused because you're carrying around this minus t0, and what is the time axis? It's not clear anymore. Right, so what my recommendation is you define z of t or z of n to be the delayed signal. So that is, you'll say x of t minus t0, and I'll say this is z of t. And then I'll refer to everything in terms of z of t, because that's the new time. So if I say that t0 is 1 day, 24 hours, then z of t is the delayed version of x of t, right? So we have a x of t which say looks like this, and then we might have z of t. Z of t might look like this triangle, right? And here's t0. But now we're thinking of this. This is the same time axis. These two exist in the same time system, if you like, time scale. Okay, so let's take an example. Let's look at the modulator that we saw for amplitude modulation. So here, this x of t is multiplied by this cosine. If we look at that system, we might think of it as x of t goes into this oscillate, is multiplied by this oscillator, cosine 6,000 pi t. So what is that? That's at 3,000 3,000 hertz, or 3 kilohertz. So this is 3 kilohertz. And then what we're going to get is y of t. So that's our original system. So now what happens if I delay x of t? Well, I'm delaying the x part, the input part, right? This input part is getting delayed, but this cosine is not getting delayed. I mean, I guess I should. This cosine part is not getting delayed, right? This cosine part exists independently of the input. So what does that mean algebraically when we try to do things? Well, if I say I'm going to apply h to x of t minus t naught, right? So this, remember, is x of t minus t naught. But I'm going to keep it as z of t so that I don't get confused. So if I look at the system definition is that the output is whatever the input is times cosine 6,000 pi t. So this c of t, I'm going to multiply it by 6,000 pi t. Now I can substitute back in my definition of z, and I'm going to get this equation, right? And what we notice here is that the cosine part is not actually getting delayed, because just because the input is delayed doesn't mean the cosine part that is inside the system, that is operating on its own little oscillator clock, that part is not getting delayed. So this overall thing is not equal to the overall delayed system, right? So if I say y of t minus t naught, I'd have to also delay the cosine. So this thing is equal to this thing is equal to y of t minus t naught, right? And so these two things are not equal, so this thing is time varying. Now something completely different happens if I put the x inside the cosine. So if I look at it, we'll look at a discrete time system where I have the cosine 3 pi over 4 times x of n, right? Now this system is not linear. It's actually a very weird looking system if you think about it. I recommend trying to simulate it. You might see it's kind of it does some weird stuff. A little confusing to think about. But again, we can do the same trick analytically, right? If I want to understand what's going on, I'm going to say z of n is equal to x of n minus n0. Then I say h of z of n. So I'm just going to plug in z of n for x of n. I'm going to get cosine 3 pi over 4 z of n. But then if I translate that, that's equal to cosine 3 pi over 4 x of n minus n naught, right? But that's equal to y of n minus n naught. So this thing is time invariant. It's not linear, so it's not like the system that we like to work with, but it is time invariant. So this shows you that these properties of linearity and time invariance are not always, they're not always together. You can have systems which are linear and which are not time invariant, and you can have systems which are time invariant but nonlinear. And so these two things are separate. In general, all of these system properties are kind of different from each other. So just as a thing to try yourself at home, you try to determine if each of these systems is time invariant or time varying, right? We could look at a system that squares its input. We could look at a system that multiplies by the time step, the current time. you can think maybe the second one you might suspect that it's time varying, right? Because the input depends on the output depends on whatever n the current time value is. On the other hand, how do you show that, right? That's the real trick. You have to figure out how to prove it. Then you have y of t is x of t minus 2, and then x of 2 minus t. So there's a kind of time reversal going on in there. If you take y of t as x of 3t, that's a speed up. Or is speeding up the signal? Is speeding it up time invariant or time varying? It's hard to say off the top of your head. You have to go through the analysis and figure it out. And finally, if you look at the even part, so this is the even part, what if I just look at the even part of a signal? Is that time invariant or time varying? So I challenge you to look at these questions. I think by going through the exercise of trying to show that they're time varying or time invariant, you'll understand that concept a lot better. And it's important because for most of the rest of the class, we're going to be talking about linear and time invariant systems. So try it at home and let me know what you find out.